Martin, we are very delighted to have you here with us today, and a very, very warm welcome. The floor is yours for your talk.
Thank you very much, and welcome to everyone. So I'm honored and pleased to take this opportunity to talk to you today. And the first thing I'd like to say is that I'm not going to show any slides. And you may be surprised about this because typically in scientific environments, the first thing that people do is present a slideshow. I'm not going to do that today because of several reasons. One is to take you by surprise, and I hope I succeeded with this already. The second one is that I'd like you to really focus on what I'm talking, and slides often have the tendency to just distract you from the oral part of a presentation. The other reason why I'm not showing slides is that you can find a lot of what I'm doing in all kinds of animations and sequences, and really the only visuals that people can show when they do modeling is either something boring like a model architecture that only people who are really deep in the subject can understand, or it's all these animated weather fields. And for this, I can just refer you to all kinds of operational weather centers or other websites that show these kinds of plots in abundance. You can also use all the weather apps and everything, and all of these have wonderful animations, and I can't produce them better. So that's why I decided to not show any of them. Now, who am I? I'm a scientist. I studied physics, first in Bonn, then in Heidelberg. This is a long time ago. At the time, we didn't have bachelor's and master's, but rather a diploma. So that's my first degree, a diploma in physics. And this was actually solid state physics, what I did back then. But even then, I was already maybe even more fascinated by computing and programming than the actual physical laws and the physical experiment, even though I really loved also building these cryostat experiments and designing stuff there. But the programming was really what fascinated me most, actually. But then after my diploma, I was kind of getting a little, well, maybe not bored, but I felt that this topic that I was working on in solid state physics was a bit esoteric, and I wanted to do something more meaningful. Also, I felt some sense of responsibility for society, and so I figured, well, maybe environmental science is the way to go. And then I was looking for a PhD position and actually found one here at the research center in Jülich. And even though I was a physicist and had no clue about chemistry at all, I ended up doing atmospheric chemistry. And once I started with that, I came to like it so much that I decided to make this the basis for my career. Now, in this atmospheric chemistry work, I also started out first doing experiments. So we were measuring peroxy radicals, and there was a lot of fun building instruments and other things. But again, relatively soon, it became clear to me what I really like to do is analyzing data, looking at the bigger picture. And so I started collecting trajectory information at the time. I started to do chemical box modeling and putting all of that together then in my PhD thesis. From there, the almost consequential next step was to go into 3D modeling. Note that in the end 1990s, the computational capabilities and also the models themselves were still at a relatively early stage. And I was at a postdoc at the Harvard University. And there I contributed to building their first chemistry transport model. I developed a tool suite for evaluating the model and analyzing the output. And this tool suite, I'm very proud to say, actually lived on for at least 20 years or so, even after I left. So it kind of changed the way they were working. And I also dealt a lot with observational data from aircraft campaigns. And this was actually a lot of fun participating in really large US aircraft campaigns where people used an old passenger aircraft, which was then equipped by the NASA to become a research airplane. And I was lucky enough to participate in one mission that went to the South Pacific. So this was a really great life on all kinds of places on this planet. My job was not really to do an experiment there, but to collect all the data and bring it together, develop software that you could actually analyze different measurements on different time frequencies together and that kind of stuff. Things that may sound trivial to do for you today now. With all the libraries that are available at the time, you basically had to still hand program these things. Now, with these first steps into 3D modeling, I went on to become another postdoc at the Max Planck Institute for Meteorology in Hamburg. And here I assumed responsibility for building a chemistry module for the climate model. At the time it was called ECAM. And so there was a lot of, again, coding, software development needed to really get this model running and in place. So we started out with an existing chemistry transport model, so a so-called offline model, and then extracted the chemical routines to bring them into the climate model. But there were many pitfalls and stepping stones that we had to take in order to arrive at a good modeling system. Also, at the time, I invested quite a bit of work into trying to harmonize and improve the general model infrastructure, in the sense that it became easier for people to specify the input data they wanted to use, or the kind of emission data sets and other things, so that the model became more manageable and therefore also much less error prone, because it was one of the lessons I had learned over time, that the more you leave to manual steps in the workflow, the more error prone this is. So after Hamburg, I was actually invited to come back to the Forschungszentrum Jülich to lead a group there on chemistry climate modeling. And this went on for about 10 years before I eventually, and now indeed I should probably say, got a little bored by classical conventional modeling, because I had the feeling that there is a lot of work that needs to be invested to make really marginal progress with these models. You can do only so much in terms of improving parameterizations. There's only so much you can do about improving the chemical mechanisms. They can become a lot more expensive and detailed, but you don't really gain much in terms of accuracy and precision. And so I started to look around for some other activities. I still had a lot of interest in also analyzing measurement data, and we started building a database, which is now one of the world's largest collections for air quality data, the so-called TOR database, Tropospheric Ozone Assessment Report. I will come back to that later. And through building this entire data infrastructure, we also then started building common analysis services that you can run over the web, and this is still available today. But this wasn't fulfilling me completely, and so I thought about other things, what I can do instead of the conventional modeling. And at the time, really, machine learning made their first real breakthroughs. So this was the time when machine learning appeared in the press. And a few years earlier, there was this paper that for the first time demonstrated that machine learning models can be better in image recognition than humans. And this sort of prompted me to investigate that field a little better. And in fact, I started a group then at the Jülich Supercomputing Center. So I switched institute within the Jülich Helmholtz Center. And there I was lucky enough to immediately win an ERC Advanced grant called IntelliAQ, where we explored then state-of-the-art machine learning methods for the analysis of air pollution data. And this was a lot of fun and great to work with a team and to really gain insights into what works, what doesn't work, and how to do this actually. At the time, there was still a lot of skepticism in the earth science community about machine learning. There were some professors, even older than I am, who claimed, well, they had done it in the 1960s and it never led anywhere. But my recognition was that, well, that's probably not true, because machine learning of the 1990s is really just statistical science, whereas the breakthroughs that came after around 2013 or so are really due to much more complex data architectures, much larger amounts of data, and completely new concepts and methods. And indeed, not only with our air quality work, but also in the meteorological community with weather forecasting, the field really picked up very rapidly. So I still remember a workshop in 2018 where I participated in Oxford in England. And we had about 60 people in the room, and there were maybe 3 or 4 who believed in machine learning. All the rest were extremely skeptical about it. And then we wrote a paper in the Philosophical Transactions journal where we analyzed a little bit what would be the issues that need to be tackled in machine learning in order to make good quality weather forecasts. And it turned out that for all of these issues that we saw, there were already some machine learning solutions on the market. I mean, they weren't yet coupled together, and so no one had at the time demonstrated that you can do weather forecasting with machine learning. But it occurred to us that, well, it should be possible. It will probably only take some time. And to be honest, at the time, I was expecting that this would maybe take 3 or 5 or 10 years before we are there. But I completely underestimated the pace at which machine learning was actually developing, because only 2 years later, basically, we saw the first papers appearing that showed weather forecasting results that were at least similar in quality to what was then operational with respect to the classical numerical models. And so this, of course, really gave my research a complete boost and really made it ever more exciting. Unfortunately, I have to say that there wasn't any further funding for continuing the air quality work with machine learning. So I hope that this will change again in the near future. But at the time, there was really a big run then onto weather AI. So applying these modern machine learning, deep learning concepts to weather data. And then soon after, people also began looking into climate aspects. I will discuss those aspects a little more in a short while. And then through an invitation that I received to a workshop in the US in 2021, I met a colleague who's now at ECMWF leading a machine learning group there, Christian Lessig, and he had this initial idea, and I joined forces with him very quickly to actually develop a foundation model for weather. And so we built a small prototype of that, basically among 3 people primarily, with a little help from some others, which became a first foundation model for weather. Unfortunately, it never got published, but there's an archive preprint available where we explored this concept, and it actually turned out to work in principle at least. But having this demonstrator really led then to almost a surge of funding. So we were lucky enough to gain projects from the German ministry, from the EU, from Helmholtz, so the Helmholtz Foundation Model Initiative, to continue this research and build upon this. And now I'm leading a team of 20 people, and altogether we are about, I would say, 40 to 50 scientists and software engineers who are building the so-called weather generator model. That's the baseline for all our foundation model activities. And that's, of course, a fascinating development that you, from this very small conceptual thing, you end up really leading, managing a large team to build the next generation weather and climate model. Let me describe a little bit what are the issues with machine learning for weather before I then want to continue a bit with some aspects about my career path and what's important or has been important in my career, for my career. So the general issue is that we're very used to numerical forecasts. And what they do is they take an initial condition of weather data or climate data that they then use to advance in time. You need to discretize the Earth or the Earth atmosphere, both spatially and temporally, in order to be able to numerically solve all the governing equations that describe the conservation of momentum, energy, and mass in the atmosphere, or more generally in the Earth system. And then you basically need to solve all these equations in many, typically these are by now some 10 or 100 million grid boxes that are used, and you need to solve these equations at every time steps at all of these grid boxes. So that's a massive compute problem that really requires massively parallel computing and all kinds of engineering tricks to make that efficient. However, the deficiency of these numerical models is that even though you throw a lot of compute power into solving the problem, you still are limited in the resolution that you can actually afford. And typically for global models, for global weather models, this is now on the order of, let's say, 2 to 10 kilometers. But if you look around, you will find that on a scale of 2 kilometers, there's a lot of variability. There can be some small mountain, there can be some high-rise buildings, there can be a small river or small lake, anything. Also, a cloud might even be smaller than sort of 2 kilometer diameter. So therefore, there's a need to parameterize smaller scale processes. And this means that people are using information from field campaigns, some other derivations, some assumptions and all of that to try and describe these small-scale processes. And these are the so-called empirical parameterizations. And as you can imagine, they're always very crude and honestly mostly wrong. So for example, with turbulence, at least for the most part of when I was still dealing with these models, all the turbulence parameterizations were based on a couple of field campaigns that were done over flat terrain. But if you look around and want to evaluate the model in the Alpine region, for example, then certainly that's not flat terrain. And indeed, we know that turbulence behaves quite differently in a mountainous terrain. So that's one key area where such a parameterization fails and simply produces wrong results and biases in the model. Now, what machine learning does is sort of the complete opposite take on this. So machine learning takes existing data. This can be data from numerical models. Indeed, most of the existing models have been trained primarily with numerical model data at first. But more and more we see now that you can also make direct use of observation. So you can use satellite data, station data, or even data from aircraft sensors to directly sort of estimate the state of the atmosphere, also with a machine learning model. And then the machine learning model is trained to do a similar thing as the numerical model to make a prediction. However, it can be trained directly to make a prediction on a longer time step. So for a classical model, it depends on the resolution. There's the so-called Courant-Levy-Friedrichs criterion, which basically states that your time step length must not exceed a certain amount that depends on the spatial scale. I always like to equate that with a simple example that the wind shouldn't blow over a complete grid box within one time step, otherwise the model becomes numerically unstable. And so this means that at a scale of, say, 1 kilometer, you need to go down to time steps of a minute or something like this, which is really short. And that, of course, also leads to error growth, because if you have a very small error at every time step, this error accumulates pretty rapidly over time. The machine learning model, in the contrary, can be trained specifically to make a forecast for a specific time step in the future. And this has been exploited, for example, in the Fushi model, where they have built 4 different variants of the model that were trained on time steps for 1 hour, 6 hours, 12 hours, and 24 hours. And then you can basically couple those together, and you avoid the error accumulation at these individual time steps. So this is one aspect why machine learning models actually can perform better than numerical models. Another aspect is that they do basically intrinsically incorporate all these small-scale effects, in particular if they are trained directly from observations, or if they include observations in their training. And so they avoid these biases that are induced through the numerical parameterizations in conventional models. Having said this, there are very fascinating developments going on these days that actually lead us also to reflect fundamentally again on what are we actually doing when we model weather, in the sense of what are our assumptions, what are known facts, what are also our evaluation goals, so what are we aiming for, and how can we get to achieve these things. And this is where machine learning models really add a very different perspective to the field, and really make also classical models rethink what they have done in the past. And so one way that can be potentially fruitful in the future is also a blend of these different worlds. So people have experimented with using machine learning models as parameterizations in large-scale models, or also to supplement or replace certain components of a classical model through a machine learning model. For example, you can replace an atmospheric chemistry scheme if you want to do air pollution forecasts, and basically have a conventional weather model coupled to a machine learning chemistry model, and these kind of games can be played. Now, weather, I would say, is somewhat solved in the sense that we know how to do this with machine learning. It's a relatively straightforward problem, also in the time scale that we're looking at least for medium range weather forecasts up to 2 weeks or so. This is a problem that works very well, and indeed numerical centers or operational weather centers like the German Weather Service or the European Center for medium range weather forecasts, who have now offices in Bonn. They are now deploying machine learning models for their operational weather forecasts more and more. At this time, they're still running them in parallel to numerical models, but I guess it can be expected that not too far in the future, they will rely solely or at least primarily on the machine learning models for their operational and daily forecasts. It's a different thing if you come to climate, because climate is acting on much longer timescales. So in climate, we're typically interested in timescales from at least seasons over decadal timescales, if not to centuries, or in some cases even much longer. And here we face several problems and challenges with machine learning. One of them is the data scarcity. So unfortunately, we did not have satellites in the 1800s or 1900s, which makes it very difficult to constrain any simulation and to generate training data that the machine learning models can use. The other aspect is the complication of the feedbacks between the different components of the climate system. It's the climate system is not just about the atmosphere. It's clearly very important to cover many different aspects, like the ocean, like the terrestrial land, including the vegetation, and then also the carbon cycle between land and ocean and atmosphere. There are aspects in the cryosphere, so the ice shields and glaciers that play a role for climate. And all of these different components or compartments, as we say, they're coupled with each other through various processes. And these processes can interact at very different timescales, ranging from minutes to centuries even. And this is something where we don't really have a recipe yet how this can be captured with machine learning models. So if you're interested in building a career as a machine learning climate scientist, there's clearly a lot that will need to be done, and that will probably last for at least several years into your careers, even though, as I said before, I've been wrong once in terms of making forecasts into how long it will take. So these aspects are now the big problems we're trying to tackle in various projects, in particular in the Helmholtz Foundation Model Initiative project HCRIMREP, where we are using the weather model weather generator to first extend it to longer timescales, but also couple it with some of the Earth system components. So we are coupling an ocean model to it, and we are also coupling an atmospheric chemistry component to it, and extend the model into the stratosphere. And we are actually just organizing a workshop where we want to investigate those really fundamental problems that we need to solve in climate AI science. Now, I'd like to come back to a bit of my career perspectives here. So if I look back from what I achieved, I think there are a couple of things that are lasting in the community. So one of the things that I'm kind of proud of is a review of biomass burning that I did in the context of a first large project that I coordinated. It was called Retro. And again, it was one of those things that lasted for several years. So it was a huge work to compile all that information from literally hundreds of papers and looking at all kinds of data sets and trying to fuse things together to generate an inventory that can be used to simulate biomass burning emissions in chemistry transport models for long-term simulations. And this inventory indeed has been used for at least 2 cycles also of IPCC. So this was quite a long-lasting effort. Another thing, and this sort of brings me back more into the kind of information science aspects of my work, we built at some point for another model intercomparison activity. This was long-range transport of air pollution. We built an intercomparison platform because at the time when we wanted to pull these different model results together, we found out that they're all not intercomparable or interoperable, as people would say today. So all the metadata was very different, the grid structures were different, and so on and so on. And so we basically set up various scripts and things to harmonize all these model data and made it possible to really pull the information together and get a joint evaluation of all these models. This was also something that was highly well regarded in the community. The other thing then is the TOR database that I mentioned earlier. So this has really evolved now into, I would still claim, one of the most fair data ecosystems that exist. So we've spent a lot of effort and time into really looking at the FAIR criteria. So making data findable, accessible, interoperable, and reusable. And really try to build all of that into our data infrastructure, including, for example, a web link that allows you to generate a citation string from a request that you made earlier in order to process data. So that's basically as far as we take it. And also trying to really make it user-friendly and easy to use, how to get the data. Another very important aspect is versioning, so that whenever we replace anything in the database, there's a log and a protocol. So you can always trace back basically what changes happened since you last accessed the data from the database. And this platform is also now actively used to train machine learning models. So this clearly is, again, building a foundation for work that others can do, or also we ourselves can do to advance research. And then, the last thing I'm really proud about, of course, is that I can consider myself an early adopter of machine learning, and particularly also foundation modeling. And it's really a wonderful experience. I'm just very, very happy that I lived through this to see such a fundamental change occurring during my career. I mean, it's really, I think, mind-blowing that you enter a field, you learn about how things work and how people do their jobs and how they find out new things. And then suddenly comes a new tool and a new way of approaching the problem. And the whole field is basically getting overruled. And if you're riding this wave at the forefront of research, this is just a wonderful feeling. So if you ever get a chance like this, take it and be happy there. I'd like to end my little speech here with a couple of general lessons from my career. I mean, I'm almost nearing completion of my career now, so I guess when you guys will have at least finished your PhDs or are in the middle of your postdocs, I'll be happy retired and growing potatoes or something. And so I think I'm old enough to make some recommendations. And the first one that I'd like to share is, and that's one thing I had to learn myself, I must say, and that was hard at times, that you have to go all in order to be successful. So I guess many of you know these situations with non-permanent contracts and having to think about, okay, how can you basically survive the next 3 years and what do you do afterwards and so on. But the key thing is, don't let yourself be too much distracted by that, but rather really live for your idea. And well, of course, there's always a risk that you will fail, but then also take the consequence and leave science. But other than that, if you are successful, then of course it can be a really rewarding career as a scientist. But I think the lesson is you can only be successful if you really put all the eggs in one basket. Nevertheless, I mean, this of course requires some confidence about yourself, but the second lesson that I think is truly important and really distinguishes, I would say, good scientists from not so good scientists is that you're always doubtful about your own ideas and your own results. So before trying to blame anyone else, blame yourself. And indeed, probably 90% of what you produce is rubbish. And in order to make sure that the 10% that are good are really good, you really have to scrutinize your ideas and your results. Really question yourself all the time. Was it really the right thing? Was this the right idea? Was this the right approach? Are the results robust? Are they plausible? And all that. Do that all the time. Always question yourself once more. Even if you think this is great, ask another question. Is it really true? Right. The third lesson, I think, is communication. So really communicate and don't feel shy to also approach the big shots. So that has been one thing that I think drove a lot of my career, to really always reach out to people I was looking up to. And I was really happy then, as soon as I discovered some flaws in their arguments, I kind of had the impression, okay, now I know that I've understood something. So I think this is something that can be quite helpful. To really try to challenge also the big shots. Don't be afraid of them. Don't feel shy. They like to discuss with young people and exchange ideas, and they're thrilled if people are really coming forward and raising ideas and bringing things forward. All right, and then a final thing that I'd like to mention is, at least for my career, it has been fundamental that I was always a techie in a way. So I was always very much interested in technological developments. I mean, at the end, this was what led me to start with all the machine learning work, but also before, all the computer science stuff that I've been doing has been quite influential, because I discovered that you can do a lot more if you master the technology. For example, at the time in the early 2000s, when we were doing this hemispheric transport of air pollution comparison platform, most people were able to really just only work on small data sets, and they really had no clue how they could handle gigabytes of data so efficiently. And so looking into this and really mastering these kind of technologies really gives you an edge, because not too many people can do it. And if you can do it, you can produce results that are much more impressive, much more robust, and much more meaningful than if you have to, from the start of your work, limit yourself to some small area or case study or whatever. I don't want to discourage you from doing case studies. They can be very meaningful and valuable to get new ideas and find out new things. But in the end, at least according to my experiences, you can always generate a lot more impact if you think big and if you're able to actually work big. And with that, I'd like to close.